Okay, so oh, I didn't turn it on. All right. Can everybody hear me? Yeah. I'm Kesha. I'm from the University of Maryland.
I'm Kartik from University of Chicago.
And we're going to be talking about our work on a verified circuit optimizer. So the end goal of this project is a verified compiler stack for quantum programs. So this is my very high-level view of a compiler stack. You start from some high-level language like Quipper or Q#, like we've heard of so far. You translate that into an IR. Then you do some optimizations on that IR, or maybe circuit mapping to get it to match requirements of a particular architecture. And then you convert that into hardware instructions. And so we're actually, in this talk, going to be focusing about this middle part, which just takes your unoptimized IR, which describes a quantum circuit, and turns that into a different quantum circuit, probably optimized in some way. And these check marks here are supposed to represent that every transformation is formally verified to be semantics preserving. So that means that whatever program you start with, the program you get at the end of the transformation has the same meaning. You don't want your program to introduce behaviors that the programmer didn't intend. And we're going to be doing this in Coq. So those of you who are familiar with CompCert, think of this as our goal is CompCert for quantum programs. So we're going to be talking about VOQC, which is a verified optimizer for quantum circuits. It's built on top of SQUIRE, which is our small quantum intermediate representation. As you can tell, we have a fondness for acronyms. It's implemented all in Coq. It's about 8,000 lines of Coq code with 1,500 for core SQUIRE and the rest for the VOQC transformations. And there's also about 400 lines of standalone OCaml code for parsing and translating OpenQASM. We actually extract all of our Coq code to OCaml and compile it as a binary, so you don't need to know OCaml or Coq to use VOQC. You can just give it an OpenQASM circuit description, and you'll get back an optimized OpenQASM circuit description. And so here's the slightly revised diagram for what we're talking about in this presentation. We assume that you convert from a high-level language to OpenQASM, as you do with standard compilers. Then you convert from OpenQASM to our intermediate representation SQUIRE, which is going to be similar to OpenQASM, but it is more convenient for us to have an IR that's in Coq. We're then going to do verified optimizations with VOQC to get out an optimized SQUIRE program. And then you convert back to OpenQASM and continue your compiler toolchain like normal. So here's what SQUIRE is. It's really just a reduced version of OpenQASM. There's nothing particularly fancy in it. We've split it into sort of two parts. The unitary core allows unitary gate application and sequencing. So this is just, think of it as a list of unitary gates. Our full SQUIRE allows also the no-op skip and conditional measurement. So this is kind of a classical control where you measure qubit Q, and if you measure 0, you execute program P2, and if you measure 1, you execute program P1. Defining the semantics requires that you know the size of the global qubit register. So we're assuming that there is some number of qubits that you have access to, and that doesn't change throughout the program. And you need to know what this number is in order to compute the semantics. So just say it's D for now, then a unitary program is going to have a semantics that is a unitary matrix of size 2 to the D by 2 to the D. And a non-unitary program is going to correspond to a function between density matrices. And so, oh my gosh. What did I do? Kartik, help.
Let's play again.
Oh, that's scary. Okay. So this is the definition at the bottom. There's nothing new here. This is the standard denotational semantics people have used in the past for quantum programs. On the left is the unitary semantics. Sequencing of unitary gates is just matrix multiplication. And then the denotation of a single gate we're going to define in terms of this apply function. And what apply does is nothing fancy. It just extends the gate you want to apply to the entire space of the global register. So if I want to apply an X gate to qubit 5, then the denotation of that is the X matrix, 0, 1, 1, 0, applied to qubit 5, and then identity matrices applied to everything else. So it's padded with identity matrices. And similarly for apply 2, the denotation of non-unitary programs is functions over density matrices. So skip is a no-op function, the identity function. Sequencing is function composition. And on the last line there we have the denotation of measurement, which again, this is standard. This is not something that we came up with. It's going to be the sum of the denotation of the program P1 applied to the case where Q is in the 1 state, and the denotation of program P2 applied to the case where Q is in the 0 state. So we have a variety of transformations implemented within VOQC. We've spent most of our efforts so far on unitary transformations, which is optimizations of unitary programs, so programs without measurement. Most of our optimizations are inspired by a recent circuit optimizer by Nam et al. For the most part, they include, most of them are gate propagation and cancellation rules, which are really just peephole optimizations, where we replace a subcircuit, we identify a subcircuit in the program, and we replace that with an equivalent subcircuit. But then we also have a more advanced optimization called rotation merging, which is not really peephole optimization because it allows you to combine Z rotation gates that aren't necessarily adjacent in the circuit. And it does this by looking at the phase polynomial representation of the circuit. We also have a few non-unitary optimizations. Probably the fanciest is classical state propagation. So you saw that our measurement is a conditional branch. So if you're in the branch where you measured qubit to be in the 0 state, then you know that if you measure it again without doing any more operations, you're still going to get 0. And you know that if you do a control with that qubit, you do a controlled NOT with that qubit as the control, that's equivalent to a no-op, so you can remove that gate from the program. We also have a pass that removes Z rotations before measurement. So another important part of quantum compilers is this kind of idea of circuit mapping, which we're going to think of as the problem of, I have an architecture where 2 qubit gates are only possible between certain pairs of qubits. They're not possible between every pair of qubits. And so I want to transform my programs such that they respect all these connectivity constraints. And so we have an implementation right now that is really the most naive circuit mapping possible. It takes a description of a graph and a program, and it maps that program to that architecture by whenever there's a 2 qubit gate, it moves the qubits closer together via swaps, and it moves the qubits back to their original location. This is kind of the simplest thing you can do, but it's done. Yep, and so this is what we have in VOQC so far. And I'm going to be talking mostly about unitary optimization since that's where we put most of our effort so far. So as an example of one of our unitary optimizations, this is XIZ propagation. The goal of XZ propagation is to take X and Z gates in the circuit, propagate them as far right as possible with the goal of canceling them out. So I start with the circuit in the upper left, which starts with an X gate. I can commute that gate, and I can apply a series of equivalences here to commute the gate right to become a Z gate. Then I can commute the Z gate through the control of the C naught. Then I can commute the Z gate again through an H gate to become an X. And now there's 2 adjacent X gates, which cancel each other out. So what I end up with is this program in the lower right that is equivalent to the program I started with, but uses fewer gates. And so because we're working within Coq and we want something that is extractable to OCaml code, we rewrite all of our functions in Coq fixed points. And so we're writing our transformations in a functional style. So here at the bottom of the slide is a really simplified version of what propagate X looks like in our code. So propagate X is a recursive function that takes a qubit Q, which is the qubit I'm propagating on, and LST, which is the remainder of the program. So in my example at the top of the slide, Q is 0, it's the top wire, and LST is everything from the first H gate rightward. And then I'm going to match on the structure of the remaining program. So if there's nothing left in the program, I'm going to just put that X gate at the end of the program. If the next gate in the program is an X, I'm going to cancel with that X. If the next gate in the program is an H, then I'm going to propagate through that H and transfer control to the mutually recursive propagate Z function, which is not shown here but has a similar definition. And so in the picture above, the first transition corresponds to the third rule in the program, and the last transition corresponds to the first rule in this pseudocode. So what we want to prove is semantics preservation. This means that for any program P, the transformation applied to P has the same denotation as the original program. And this equality here might actually be up to a global phase. And so this works reasonably well for all of our peephole optimizations. We found that for some of the more sophisticated optimizations like rotation merging, it's also convenient to be able to prove that, to do this proof by proving that T of P and P have the same output on every basis state. For circuit mapping, along with proving that the transformation is semantics preserving, we also want to prove that the output program actually respects the constraints that we said it was supposed to respect. And proofs are fairly straightforward by induction on the program P. So here's again, kind of a high-level example of what this looks like in our code. So for the propagate z function we had before, we want to prove the property that the output of propagate x is the same as x concatenated with LSD. And so the reason for that is that I start with my program that is x and LSD, and I want to do something to that produces an equivalent program, but hopefully it cancels that x gate. So the first case of my proof is the base case, and it kind of holds trivially. The second case is also base case, but a little more interesting. We can see that if the next gate is an x, then I just return the tail of the list. And the tail of the list is equivalent to having put 2 x's at the front of the list, because 2 x gates will cancel out. And the next 2 cases actually use the inductive hypothesis. So we'll look at this last one. So we can see that if the next gate in the program is a z rotation gate, which I've written as rz, then what this program returns is this term right here. And by my inductive hypothesis, I can replace propagate x with x followed by t. And then I can do another basic circuit equivalence to get from step 3 to step 4. And so my point is just that the proofs are fairly straightforward by induction on P, but you do need a variety of circuit equivalences like this one that says that you can change RZ dagger X into X RZ. It turns out that proving these matrix equivalences is actually a little bit painful in Coq. The reason for this is that to prove equivalences, you end up with these really big matrix expressions that you want to simplify in a lot of cases in your proofs. And so, for example, in the X propagation proof, I'm going to want to know that X commutes through the target of a C0. And to prove this, I need to prove the equality on the bottom of the slide with the expanded versions of my apply functions, which expand as follows. So just look at the top one first. It just says that the denotation of the X, applying the X gate, is just the X matrix padded by some identities. And so what's happening in this C0 denotation is it's just has 3 padding terms now, because I want to pad before the first qubit, between the 2 qubits, and after the last qubit. And now here I've shown the case where m is less than n, but you also need to consider the case where m is greater than n. And if you have more C0s in your expression and more qubits in your expression, then you end up with even more cases. So we realized fairly quickly that this was a pain point, and so we spent a lot of, and so if you do all your simplification in Coq, you'll find that both sides reduce to this expression at the bottom showing that they're equal. So we realized fairly quickly that this was a pain point, and so we spent a lot of effort automating this. And now, for the most part, our matrix equivalences are proved by one tactic in our development. So we've verified that everything in VOQC is semantics preserving. Of course, that doesn't necessarily mean that it optimizes anything, that it actually reduces gate count. So to convince you that our code is actually useful and is doing something interesting, we've evaluated our unitary optimizations on a benchmark of 29 programs. We compared against the industrial compilers Qiskit and TCAT, as well as the research compiler PISIX, and we also just copied the results, reported the results from the Nam et al. And Amy et al. Papers. We're going to look at total gate count reduction and T-gate count reduction. So these are our results. I'm reporting average total gate count reduction and average T-gate count reduction. So as you can see, VOQC is not quite not quite on par with Nam et al. Yet, because we haven't implemented everything they've done. But it's at least good enough to significantly outperform the unitary optimizations available in TCAT and Qiskit currently. We've implemented enough of Nam et al. That our T-count reduction is basically on par with Nam et al. And other state-of-the-art solutions. And the main point of this is that VOQC is fully verified, whereas these tools are not. And so we think this is pretty encouraging evidence that it actually is possible to verify interesting and useful circuit transformations in our framework. And now Kartik's going to talk about some of our ongoing work.
So Kesha talked about how we would like to have a verified compilation toolchain for quantum computing as well. And we saw how one component of this toolchain is verified, which is VOQC. But what about the translation between industry IR, such as OpenQASM and SOIR? So ideally, we would like that translation to be verified as well. So we decided to solve this problem. And to do that, we wrote a feature-complete parser for OpenQASM. Then we did translation between the unitary fragments of the two languages. Then to verify the translation, we had to develop a denotational semantics for OpenQASM, which did not exist. And then we stated some semantic preservation properties for the translation. So in the rest of the talk, I'll talk about what are the similarities and differences between the two languages. So talking about syntax, the two languages are fairly similar. As Kesha mentioned, SOIR has unitaries, which are either sequences or gate applications, and qubits really refer to indices in a global register, while OpenQASM is a much larger language. So it looks more complicated. So we have expressions that could be identifiers or identifiers with indices. Then there are unitary statements, which are fairly similar. Then there are commands to create new qubit registers or new user-defined gates. The sequencing is almost exactly the same, while gate applications, apart from single qubit gates and 2 qubit gates, we can have arbitrary gate applications. And in this presentation, I'm just showing Hadamard and CNOT, but both of these languages support arbitrary unitary operations. And I should mention that the presentation of OpenQASM abstract syntax and our development of denotational semantics is inspired by the work done by Matthew Amy last year. Talking about denotational semantics, we saw SOIR's unitary semantics before, where a program corresponds to a unitary matrix. In case of OpenQASM, again being a larger language, we define values and environment and a quantum state, where values are locations. They could be location arrays, or they could be unitary gates, which look like functions. Then the environment is a mapping from identifiers to values, and the quantum state is a 2 raised to d dimension complex vector, which represents the total quantum state available to a QASM program. Here we see some of the specifications of the 3 syntactic classes. So environments take expressions take an environment and return values. Unitaries take a quantum state as well and modify the quantum state, while commands can also modify the environment. And I've elided a lot of details here, but the point of the slide is that the unitary semantics in OpenQASM and SOIR are almost the same. Even the apply functions are the same. Talking about the translation, we have 2 functions, f and g, where f is the translation from SOIR to OpenQASM and g in the reverse direction. And the property that we state is for any program in SOIR for a certain dimension d, its denotation will be the same as the denotation of the translated program, and same in the reverse direction. Further, we can say that if we start from SOIR and translate to OpenQASM, and then go back to SOIR, we can recover the original program. But note that the reverse direction doesn't hold, because our translation is lossy from OpenQASM to SOIR, because SOIR doesn't have a concept of variables. And a byproduct that came out of our work is OpenQASM parser that we wrote in OCaml. It conforms to the spec that was published by IBM in 2017. We use OCaml lags and manheat for writing this parser. And as of 2 days ago, our parser is available as a library on OPAM package repository. So you can install it, and if you'd like to manipulate OpenQASM ASTs, you can do that.
There's tons more to do, right? We don't have a full featured compiler right now. We're really interested in incorporating other optimizations from other compilers. We're especially interested in looking at optimizations that reduce error and proving that those actually reduce error as intended. That would be really cool. We're definitely looking at more sophisticated circuit mapping algorithms. There's a lot of current implementations that we can borrow from, like in KizKet and TCAT. We also have some preliminary work on compiling Boolean functions to classical circuits and proving that's done correctly. And then as with any large project, we have a long list of things we'd like to improve with the performance and the automation and evaluations on larger benchmark sets against more compilers.
We would also like to expand the verified toolchain. More specifically, we haven't covered the non-unitary fragments of the two languages in our translation work, so we would like to expand that. Our parser is not verified, but like ComSurf, we would like to verify it using Manhage's Cog backend. And then it would be ideal to have verified translation from higher-level languages such as SOIR and Q# as well.
So in conclusion, we've presented our compiler VOQC, which is built on our IR SOIR. Both are implemented and verified in COC. And our performance seems to be comparable to the state-of-the-art compilers. We also want this tool to be usable, so we've provided the ability to translate between SOIR and OpenQASM. There's a lot of ongoing work. Let us know if there's something that you think we should really implement, or if you're interested in working on VOQC. Our code is available online. The top link is for VOQC and SOIR. The bottom link is for OpenQASM parsing. And a draft of our VOQC paper is available online. Thank you.
Okay, we have time only for quick questions. Any quick questions? Okay.
My question is, now that you have semantics for at least part of OpenQASM, what is the benefit of using SOIR as opposed to just doing the optimizations in OpenQASM?
So I think we actually would like to do things on OpenQASM directly. The reason we started with SOIR is because it was easier to define a small language that we could clearly define the semantics for in our language. But I think like all of the work we've done would more or less extend to OpenQASM, or rather our embedding of OpenQASM in COC, which would look a lot like SOIR.
Thanks. So to prove the correctness of the rewrite rules, you need to compute the whole matrix for the unitary.
So
is that correct?
Sort of. I mean, so we are using the matrix semantics.
Yeah. So
right?
my question is, in practice, what's the largest one you have to handle to deal with these rewrite rules?
So the reason I was going back is because if you look at this expression, it is describing a big matrix, but it's describing it kind of abstractly. I haven't specified what these variables are. And so when I'm reasoning about matrices, I'm reasoning about them symbolically like this. I'm not actually representing a huge matrix.
Okay.
And so in terms of, yeah, and so usually when we have to actually talk about matrices as matrix objects, that's when it, usually there's smaller things like this and it's not too hard. But when we do it like in the proofs, it's symbolic enough that you don't ever have to worry about that.
Okay, thanks.
So practice 2 by 2.
In practice, like the hard proofs are the ones like this. But in like the inductive case, the things are symbolic enough that it works out pretty nicely.
Okay, we are running into the coffee break, so you can use the coffee break to keep the authors from having coffee by asking questions, and let's thank the authors again.